Okay, so in the previous lecture, we wrote down U of rho and we wrote down and we said these are the Laguerre polynomials, and let's just define it. So, the regular Laguerre polynomial L of Q and the case that we are considering here okay, note.
So you should have 2 there in the W function. Have n minus 2 and minus 1. If the form is like Q minus P.
So you have to pay attention and choose the correct P is 2L plus 1, and here you
n plus, okay, n plus L.
That's an important point. Note that
so Q is not just n, it's n plus L.
It's not just any numbers that you can choose, you have to fit it to the values that you have here. Okay. I won't go through all the properties of the Laguerre polynomials, just because all it tells us is that it's a basis function, so we have orthogonality and completeness and everything else, but it's no news for us. If you're really interested, also we don't really need it here. What do we need? Basically, I will write down the full wave function of the hydrogen atom, which we have already all the ingredients. Okay, so what do we have here? All this is normalization.
What is that? Is that x? U?
2n, n plus l.
No, the one to the left. 2
kappa.
Oh, okay.
And to remind, okay, let's in a moment, let's write down the ground state. It's very instructive. Okay, the ground state has to be n equal 1 because it's the lowest energy, and m and l have to be 0 in that case. Okay, so what do we have here? Because all the dependence on R, which is not exponential, depends on L, and L is equal 0, we have no dependence beyond the exponential term. Theta and phi, we have no dependence because the 0, 0 state of m equals 0 and L equals 0 is just a constant. So we are remaining here with constants and an exponential behavior. Now, what is A? A is a combination of constants of nature, which is about half an angstrom, which is meter. So that actually defines the scale of materials.
What do you mean?
The electron dies out on the order of 1 angstrom. You don't have a probability of finding the electron further than the nucleus on a scale of 1 angstrom. If you go to higher values of L and M, which is relevant for larger atoms which have more electrons, you'll get to 2, 3, 4 angstroms. But that's a scale. That means that atoms would not be brought together to distances smaller than a few angstroms. So all material around you has a scale of an atom per a few angstroms. That's the distance in lattices in anything that you see around you. So the scale of materials, biology, chemistry, whatever you see around you comes from this A. That is what defines the scale of everything that we see around us. Another very interesting thing is you're looking on this wave function. Where is the largest probability of finding an electron?
Oh, yeah, that was about to be my question. Is there, there's a probability of finding it in the nuclei?
Actually, the largest probability is finding it within the nucleus.
Right. So that is like that's gonna be my question. How can it be?
It's a quantum particle. Why shouldn't it? Let's stop a minute and think. Why, if you have a positive and negative charge, and you have no angular momentum, where do you expect them to be?
Yeah, at the center of my.
In the middle, one on top of the other. That's the lowest energies that can be.
Yeah.
So why isn't the electron swallowed?
Due to angular momentum.
No, but we have no angular momentum. It's L equals 0.
So it should be so. Like
If-
at the
if-
highest probability.
If it highest probability, but it's not necessarily there because of uncertainty.
Yeah.
So it has some spread around it.
But does that mean that some of the electrons, like electrons with low energies, collapse to the nucleus?
No, here's the lowest energy. It doesn't collapse because you have probability of finding it at some distance from the nucleus. The Bohr's picture of orbits and electrons is wrong. You have just a cloud of probability, as usual in quantum mechanics, where the largest probability is finding it at the center.
It's like disturbing because if you think of it that way, there's like greater chance of low energy particles to collapse rather than to stay.
No,
as
but
they are.
but you do what does it mean collapse? You don't have here a measurement.
No, I mean like the electron would turn right into the nucleus,
Yes,
and
but
then there wouldn't be ions and stuff.
it can't sit exactly at the center of the nucleus because of uncertainty. It would cost it a lot of energy, so it spreads out. And because it's lighter than the nucleus, it spreads out at much larger radius than the radius of the nucleus.
Then why would I have it at the lowest energy, have the highest probability of finding it inside the...
Okay, now you have to be a bit careful about how do you define. Here it looks as if you would say the highest probability, if I choose a point, is in the nucleus. But you're asking a subtly different question. What's the probability of finding the electron at some given radius, right? And then what you should do, multiply it with 4 pi r squared.
Oh.
So if I ask you where is the highest probability of finding an electron at a given point, the highest point, the highest probability is in the center. But since you have much more points at a given radius, 4 pi r squared more points, so at a given radius, you still have a probability of finding the electron. If you ask at what radius will I find the electron, it won't be in the nucleus. So,
but it's weird because we can say like in the nucleus we can just say that we can set the radius to be like infinitesimal and then we have a point.
So let me write it down explicitly. Assume P for the ground state. Give me R, theta, and phi. So the probability is psi n, well, 1, 0, 0, okay. R, theta, phi squared, or this is a probability density, and if I want to be more exact, times r squared dr sinus theta right. This is the probability per a unit of volume. Now, if I ask you what is the probability of finding at a given radius?
We don't need.
So what I should do here?
Get rid of the omega.
Not the, get rid. Perform.
Yeah.
The integration.
Oh yeah.
Okay. But here I'm only integrating over sine theta and theta and the phi ground state R. And since it doesn't depend,
then you get 4 pi.
I just get here 4 pi. And if I plot the probability for a given so I have here a maximum. So if you're asking where is the radius, then you're back to something that reminds you of Bohr's picture. You have a given radius, and if you'll take another, instead of the ground state, let's say an L equal 1 or N equal 2, L equal 1 or something like that, it will be further out, the maximum. But still you have a probability of finding it inside. The probability distribution, not some kind of orbits that the electron circles around.
So we should actually ask, in what radius does the...
What's the radius, what's the highest probability radius to find the electron?
And not just points, okay.
Not just points. If I look only on points, it will be in the center.
But why does, I mean, I understand mathematically, but physically, why does that happen?
You have here a game between two scales of energy. One says, well, I want to be at lowest energy, right? So let me shove the electron in the middle of the nucleus. There it will have the lowest potential energy, right?
Yeah.
But to put the electron in such a small volume costs you a lot of uncertainty. So you can't do it. So quantum mechanics gives you another force that pulls you out, pushes you out. Not only the angular momentum, because here we have no angular momentum.
It's actually like the linear momentum, if you think about like the uncertainty.
Well, yeah, it tells you that you can't go, if you put it at zero position, at a very sharp position, it will cost you a lot of kinetic energy, so it compromises somehow and gets you to a point where it's not sitting at the center of the nucleus.
Yeah. Okay.
So basically, you can check up in Google or do the calculation. You have all the definition needed. So if I give you, instead of psi 100 psi 211, you still can write down the wave function. Okay, so we know everything that is to know about the hydrogen atom. Let's go and see what happens if I'm in positive energy, meaning that I'm not bounded to the potential. I'm coming with enough energy to scatter off. If I come from infinity, I'll move out to infinity. Okay, so what do we do? The theta and phi solution remains the same. I didn't touch it. I'm still assuming a central potential, which depends only on R.
Yeah.
The only thing that changed is that, as we have noted previously, instead of just assuming the solution which falls off exponentially, I can now have a solution that behaves like e to the power ikr. So I'm back to the equation on U. So I'm just copying my previous equation. So all that's changed from the previous description is, instead of having here a kappa, now E is positive, so we have K, and we have and a trivial case, or at least a very easy one to solve, is a case where L is equal 0, because I'm losing all this. And have your two possible solutions. Just second derivative is minus u. Fine. So this is u. You remember that actually we had the R function. Spherical Bessel function, and the minus is just to get us a correspondence with the definitions of the Bessel function, spherical Bessel functions, and this is remember, we have rho equals 0 has to be continuous. So we have, this has physical meaning. This diverges has no.
Because we have the origin in the problem.
Yeah. And basically, for L not equal 0, we have as solutions the spherical Bessel JL of rho, which is also equal to the Fourier finite Fourier transform of minus 1 . So the only thing I want to mention about these functions is their behavior around the origin and at infinity. So at the origin, rho very small compared to 1. Behaves like rho to the power of L, reminiscent of what we have seen for the bounded states. And for rho much larger than 1, this is an interesting result. Very similar to the J for L equals 0, but with a shift that depends on the angular momentum. It makes sense that very far away from the origin, I can see a big difference in behavior, which is dependent on L, on the angular momentum. And the only difference really is this phase shift. Actually, this becomes important in all kinds of scattering experiments because you can see what is the angular momentum of the scattering according to the phase shift. So this is something of interest. Okay, so I think I'll stop here. Until here, it's the material for the exam. Okay. Do you need a break or let's move to
whatever you want?
Okay, so let's move to quantum computing, or specifically the Grover algorithm. And what I'm trying to do here is not a course in quantum computing, that needs a course by itself. It's only to demonstrate why algorithms in quantum computing are very different than algorithms that we're used to from classical computer science. So Grover's algorithm, Grover is the guy who came up with this algorithm, I think in the 90s. Oh, this field is new. Shor's algorithm, which is a factorial, was end of 70s, beginning of 80s. So all this subject is new. Okay, so what is it supposed to do? It's supposed to emulate search. So, what is search in classical classical computer science? Let's assume you have a string of bits. Let's call it omega. This is the string you're looking for. And then you have a database. The database is filled with such strings of length n, and if we assume that you have all the data strings that are possible in this so let me use another notation here. So we have n entries in this database, which is 2 to the power of n. Now, you want to find a specific string. So what do? You pull out a string out of your database. You have some functions that tells you, is this the string that I'm looking for? So to sound mysterious in computer science, it's called an oracle function. What does it mean, an oracle? I'm pulling out some kind of string that gives me a result 1 if S is equal to W, the strings that I'm looking for, and 0 if it's not. Okay? And basically I don't care how it does this comparison. Now, for an algorithm that is built on the idea, take the first string, pull it out of the database, compare it to W, stop when you get from the oracle the value 1. How many steps do you need to find if this...
The worst case is 2 to the power n.
So the worst case n, large n, average case okay, so very simple basic algorithm. Now Grover came out with a quantum algorithm that gives you for the average for every case the result within square root of n steps. So it's not exponential speed up like you're usually hearing, but it's still a speed up compared to n. If you're thinking n could be a very large number, square root is a much smaller number. Okay, so what makes it a quantum problem? Okay, so let me just use here the symbol x instead of s because quantum I'll use s for
Spin.
no. I can now, what can I do here? I can take this problem, put it as a string of spins like we've learned, and have states that correspond to each possible string, right? Yeah. But I don't want even to go into the details of how do I build the string. So all I need is basically that I have n states that form me a base. Each one corresponds to a string. You want to see it in a more visual way, you put a spin up, spin down according to 1 and 0 and build all these states. Okay, but for me, I could have any abstract basis x which corresponds to each basis corresponds to a given string. Now I take these states, put them into a superposition. Well, superposition is the thing that makes quantum mechanics interesting. Okay, I sum up over all these basis states. Well, x equals 0 to n minus 1. And I have here this state. This is the basis of my computation. What do I want from a quantum computer? I'll give him such a state. If one of the components is the x that I'm looking for, it will give me this component. If not, it will give me 0.
Yeah.
Okay.
Wait, but
here I built it from all the components, so here it should give me back. At the end of the day, I do some computation and end up with the basis state omega, which is the one that I'm looking for.
So wait, but x, they all need to be orthonormal, right?
Right, it's a basis.
Okay. Okay.
So now I need my oracle. My quantum oracle. So I want to know what do I do in quantum mechanics? I manipulate vectors, right? That's all we did during the whole semester. So let's assume that I have an oracle operator that does the following. Works on some state x, and it gives me the minus this state if x is equal omega, and x for all other cases. It's the same idea as that I have a function that gives me 1 for the case that it fits the strings that I'm looking for, and 0 otherwise. I'm not telling you how to build it at the moment. It depends on how I build these x states. Okay? So that's one operator I need. But this is not enough for computation. What is computation? I'll take some operator and use it square root of n times, and then I'll end up with this state. Okay, so the next operator that I need the operator US. in a moment we'll understand why. Okay, so what does it do? If it's S, it does nothing. Right? Because then I have S times S is 1. 2S minus S is S. Okay, so it seems a neutral operator. It does nothing for the case that I'm S.
Yeah.
Now, so you missed the beginning of quantum vision. We're now doing the Grover's algorithm, which is an algorithm that is a search algorithm which is supposed to find whether a string exists in a database through a quantum computation. So, I'll give you a 2 minutes summary.
Okay.
I have X states which correspond to all the strings that I would have in my database. I build a superposition of these strings, of these states, simple. And now I use 2 operators. One is an oracle operator. What does it mean? In a classical search, you take a string and you put into a function and it tells you, is it the string that I'm looking for or not? Let's say it gives you a 1 and 0. 1 if yes, 0 if no. Here what it does, it inverts the state if it is the string that I'm corresponding to the string I'm looking for, and does nothing if it's not. Okay, how to build it, I'm not going into it. That's why you call it in computer science an oracle. Something that gives you a behavior, although you don't necessarily know how to construct it. We can construct it if we know what is the state you're looking for, but I'm here giving something general. Okay, so I'm using this computation 2 operators. One is this, and the other one is this guy. Now the algorithm is painfully simple. It says, operate take your state operate at R times on your
What is R?
in a moment. Operate at R times on your initial state, and what you will get at the end would be here omega.
Oh, so R should be okay.
Why, where, what? In a minute. So, and of course R will be order of square root of n. So we need only square root of n steps. Okay, let's see how this magic happens. Why implementing this operator R times on S will give you omega. So for that we need a bit of geometry. Okay. Let's define a function, a wave function S prime, which is very simple. Square root of n minus 1. A linear combination of all states except for the state I'm looking for. We don't know how to construct it, but writing it down, very simple. The normalization here is n minus 1 because we have only n minus 1 such states that are not omega. Now let's look on the scalar multiplication of these two vectors, S and S prime. Okay.
But why would you? Like, why would you project them?
Let's see.
Okay.
That's one of the biggest problems with quantum algorithms. You can't see the structure only at the end. How you construct them, you have to have some inspiration. You don't have, like in regular classical algorithms, just a set of steps that move you sequentially towards your goal. Okay, so the two normalization, let me write down S, just so we'll have it before our eyes. This is a summation of all the states. This is a summation of all the states except the ones that I'm looking for. Okay, so the normalization will give us n times n minus 1. And since here I have only n minus 1 basis states, I'll have here as a result n minus 1, the multiplication. Because they are orthogonal and only states that belong to the same vector give you 1. And you have it n minus 1 times. So the result here is square root of n minus 1 divided by. Okay, it's smaller than 1, so.
Yeah, that's. No.
It's fine.
Yeah.
Okay. It's instructful to look on it as geometry. Okay. Let me assume that I have here a axis, that here I have my target state, and here I have S prime. Of course, this is a dimension of n minus 1, but I'm drawing it as 1. Why are they orthogonal? Because omega must be orthogonal to S prime, because S prime has no component of omega in it.
Right.
Okay. So, what is S? Of course, can can have some component of omega by construction. Okay. Now in geometry, what is S times S prime?
The size time, yeah, cosine.
Cosine of the angle between them. And for reasons that I'll see, you'll understand shortly, let's call it the angle theta over 2. So S times S prime
Right, because the size of which you measure.
that's by definition. Now let's look what these two operators, if we use them on S, do actually. Okay, let's look on using the first one. Okay, what did it do? Nothing for everything that is in the direction of S prime.
Oh.
Change omega from plus omega to minus omega. So after implementing this this operator,
So it's just like rotating stuff until it's aligned. Whoa.
right, that's the whole idea in quantum computation. Doing unitary operators, meaning rotations, until we get to our target state with a probability close to 1. Okay, so this is U omega S. Just this part switch from plus omega to minus omega. Good. So this whole angle is theta. And just by geometry, just from here, theta is equal to 2 twice
Cosine.
arc sine. I did
Oh,
because I use 1 over square root of it.
Right.
Sine square plus cosine square has to be equal to 1.
Mm.
So if I know cosine, I know also sine. Okay. Now my next step is another color. I'm going and using US here. What does it mean? It means that basically if I'm in the direction of S, nothing happens.
Good, yeah.
If I'm not in the direction of S, I get here because it's not on S, so whatever was here, not in the direction of S, comes out So, what does it do? It reflects over S. So I end up my game here. Was reflected around us because the component that's outside got a minus and the component along S nothing happened to it.
Mm.
So I'm using this guy n times. So let me write it down here. So I'm looking on one rotation, rotation and reflection, US and U omega. So what happened here? I basically got here where theta is this guy. I did it R times. So I just get now let's write down explicitly what is theta, the 2 arc sine 1 over square root of n. And instead of theta, I'm writing down times 2 arc sine of 1 over square root of n. Just use the definition. The point here was mainly the rotation and reflection. Good. Now, what is arc sine of 1 over square root of n if n is large? Small theta's sine and theta is the same, right? Sine of theta and theta are the same. So it's just 1 over square root of n.
Mm.
Right? this way 2r plus 1 over square root of n. If n is large, yes, but I want that it will be equal
In 1. You want it
equal to 1, right? So r is something I can choose. It's the number of times that I apply it. Square root of n pi divided by 4 in order that I'll get here pi over 2. Sine of pi over 2 is 1. So I use this rotation and reflection, square root of n times pi over 4 times, and I got exactly, or close to exactly, omega. So I started with some linear combination of all states, performed this operator square root of n times pi over 4, it's still square root of n times, and got after it just the state omega. So I rotate here and reflect square root of n times, and I get the wave function that I'm looking for.
But how do you know that this quantum oracle might be more expensive than the classical oracle, and then you get like back to square?
That is usually the case. Nowadays, to construct an initial state, to construct your use is usually much more expensive than the classical part. But you're doing it in less number of states, of iteration. Now, Grover is a weak algorithm. It's just a square root of n speed up, right? So probably it will never be useful. But it's simple enough to show in 15 or 30 minutes. And that's why I give it as an example. If you get to somewhere that you have an exponential speed up, which is in fact Shor's algorithm, which is factorization of numbers, which is quite an order of magnitude more complicated than this algorithm, then it might be worth your while. Although no one nowadays can construct a quantum computer that will run Shor's algorithm anywhere close to applicability. Now, that's one way of doing quantum computation. A completely different way is to go at, you saw what happens here. I'm mapping states to strings. It doesn't have to be a mapping that is clear like in spin up, spin down. It's easy, but it's not necessarily. Any mapping will work here, right?
Yeah.
I didn't use nowhere during this algorithm the exact form of mapping. It would be easier to visualize for the spin up and spin down, easier to think how to construct the use, but it's not necessary. It will work for any mapping. Now, another way to approach quantum computation is through quantum annealing. What does it mean? I create a system, a physical system, let's say spins or whatever, and I map my solutions so they fit some state.
Okay.
And I do the mapping in a way that the ground state of this system corresponds to the solution I'm interested
in. So your operators can be just annihilation operators.
I just can lower temperature and bring it to the ground state. That is, let's say, how D-Wave, the company by the name D-Wave, tries to do quantum computing. You don't know what operators work, and you don't have a specific algorithm. You have just a mapping between a physical system that you know that the ground state will correspond to your to the output that you're interested. You take this complicated system, wait till it gets to the ground state, read off the ground state, and that's your solution. You have a very clear mapping, let's say in the case of the traveling salesman, the famous NP-complete problem. And of course, in experimental state, you're never sure that you're really in the ground state. If you're in the vicinity of the ground state, probably you got a solution that is good enough. So that's another completely different way to approach quantum computing. Now you have a third thing that people come and say, well, I'm not really interested in understanding a system, but I map it to a system that a physical system that I'm interested in solving. Let's say I have a system of spins. I want to know what's the ground state. Classically, it would be very complicated because you have to have 2 to the s basis states and start diagonalizing your Hamiltonian. Here you say, no, I emulate my system on a system of qubits, wait till it gets to the ground state, and I have the solution. I know the ground state. I can get some excitations and get other states in the system. So that's a third thing that people are using quantum. And actually, this is the most straightforward way. Feynman said the best use for a quantum computer is to simulate a quantum system. But this is a very niche kind of application. So that's where quantum computing is standing at the moment. A few specific algorithms that we know how to implement. The main one of them is the Shor's algorithm, quantum annealing, and simulating other quantum systems. Mapping one type of quantum system on another kind of quantum system, which is your quantum computer. So That's what I have to say about quantum computing. So I'll say a few words about the exam. First of all, it's an exam with open material. You mean? You can bring any printed materials that you want. I don't care if you are coming with a suitcase full of books and notes and whatever. No electronic devices, not that I care about the electronic devices, but it's a communication device, so there's no way to separate them, so only printed material. Now, people are not used to open materials, think, oh, great, I don't have to read it. The exam is not the point where you should familiarize yourself with your notes and books and whatever, because then you'll spend the whole exam searching for the material. So any material you bring, I suggest read it before and know where everything is. Otherwise, you'll waste a huge amount of time on searching and then not finding it.
It's gonna be that difficult?
No, it won't be difficult at all, but I've seen already students seeing us question, oh, it reminds me something, I'll take all Kohen-Tanuji, all 2,000 pages, and I'll go through it. No, you don't. It's limited to 3 hours. You don't have time to start reading Kohen-Tanuji in the exam. You don't need to, but okay. What else? As Nitai asked earlier, I'm usually trying not to put in complicated mathematics, and I'm even not extremely angry about someone who does a mathematical mistake, unless he gets a result which makes no sense. If someone is calculating the average of momentum and gets an imaginary number, that's not a mathematical mistake. If you write something like, I did something wrong, but I understand it can't be imaginary, therefore I did a mistake, that's already much better than someone just leaving an imaginary number as a result of calculation, or not normalizing the wave function, or so all the probabilities don't sum up to 1, or all kinds of things like that that should jump out to, or someone getting in a probability calculation a number larger than 1. Should understand that. It's wrong. That's not a mathematical mistake. It's a mistake in understanding. Okay, there will be 2 or 3 questions I still don't know, with some sections.
But like in the sections, because I've faced some questions like during the homework that sometimes we don't understand like what, at least I don't, what I need to do, and then I spend like long hours to just understand. Sometimes like we need in the middle of the question, when I think about it, it works. If I for some reason use some like expansion or Taylor expansion, and then I just say, okay, now let's look at some section of the space, and then I can do approximations and stuff. Would that be like clear that that's what we need to do? Because during a test, I don't think I'd be able to do that.
I would be very surprised with myself if I give you questions that you need to do approximations.
Okay. So the math would be like
approximations,
right?
is. I said that already. Approximations is quantum mechanics too. There you have perturbation theory and time-dependent perturbation theory. And the general perturbation theory, it's like 50% of the second part of the course is approximation methods.
Mm. Okay, so now, okay, good.
Any other questions?
Just, yeah. Like, I hope the exam wouldn't be that crazy.
Well, I'm not here to check if you're exceptional gifted, but I'm here to check if you understand the material. So that's what I can say. As I said previously, I try to invent new questions that are not within the usual. So it's more important to sit and understand the lectures than to try to solve all the questions that you have in quantum mechanics. First of all, it's impossible. Second, I don't think it's a good way to study. It's not like the matriculation here that you do 10 examples of a question, so it's 90% that some variation of it will appear in the matriculation.
So going to be crazy, okay. Because on the material I think I'm pretty well.
Okay, any additional questions? Don't remember even when is this exam. You have the date here?
Oh, the exam. I think it's the 19th.
19th of February.
Yeah.
Okay. Good. So good luck. If you have questions, you can email me or set a meeting or with the Mitorgel.
Okay. Thank you very much for the semester.